Hey everybody, today we are going to talk about the law of sines. So let's get started. This is the law of sines. Don't worry about maybe it looking complicated right now. I think we're going to break it down and you're going to actually be really glad that you learned it. And you'll see that it's really not very challenging at all. Basically, the law of sines is a way for you to solve any missing triangle. If you know some sides and some angles. So we'll talk about some specific examples of when you can use it. Basically, what you're going to do is you're going to start off with your standard triangle. Remember that we label the angles of a triangle with capital letters and that we label the corresponding sides with the lowercase letters. So for example, if I have angle A here, then little a is the side that's directly opposite side of angle A. So basically what it says is when we divide side A by the sine of angle A, it's equal to the sine of B divided by the sine of angle B. And that is also equal to sine C divided by the sine of angle C. So they're all equivalent to each other. So let's do the calculations for a triangle that I prepared earlier. If I called 62.2 degrees angle A, then the corresponding side would be little a, and that would be 8. That's the side that's directly across from angle A. So I can make that a fraction. I could say that little a divided by the sine of A is 8 divided by the sine of 62.2. And I could simplify that, and I get like 9.04. And I could label this angle, 33.5, as angle B, which means its corresponding side, 5, is going to be little b. So this is like the anchor here. So I can say, well, little b is the sine of B, which is 5 divided by the sine of 33.5. And we can simplify that out. And thus this leaves me with angle C. That would mean angle C is 84.3. And little c is the corresponding side, so it's directly across from angle C. And we can see that little c divided by the sine of C is 9 divided by the sine of 84.3, which simplifies down to here. Now the answers are almost the same. I know you're thinking like, well, these are all supposed to be equal. Well, don't worry. They would be exactly the same if we had used perfect accuracy. But I did not use perfect accuracy when I was simplifying here. In fact, neither did my calculator, because even my calculator is going to make an approximation, but they are equivalent. And this is how we can see that the law of sines is true. Little a divided by the sine of A is equal to little b divided by the sine of B, which is also equal to little c divided by the sine of C. The law of sines. So is this magical? Not really. If we look at this general triangle and we split it into two right triangles that share the height, we call that the side H, then the sine of an angle is simply the opposite divided by the hypotenuse. So we could see that by doing this for angle A and angle B, we could set them both equal to H. Thus we would get A times the sine of B is equal to B times the sine of A, which we could rearrange by dividing both sides. We could divide both sides by the sine of A. We could divide both sides by the sine of B. And thus we would get A divided by the sine of A is equal to B divided by the sine of B. If this isn't clear right now, don't worry. We're going to talk about it more in class. And we could do the same thing to include the C divided by the sine of C fraction. So when do we use the law of sines anyways? It's really best to use the law of sines when you have 3 dimensions of a triangle and you need to find the other 3. So you know 3 parts. And they can't just be any 3 parts either. Otherwise you won't have enough information to solve the law of sines equation. You can only use the law of sines if you're given an angle side triangles. That's 2 angles and 1 adjacent side. Or if you have an angle side angle problem where you have 2 angles and their included side. You could also use the law of sines in this situation, side, side, angle. Those are the donkey problems. They're an ambiguous case. Sometimes those problems are going to create one triangle. Sometimes they'll create two triangles. And occasionally you will even find that they will not create any triangles at all. We're not going to talk about those ones today. We're going to focus on these two, and we'll do the other kind later. So here's our first example. Let's say that we're given a triangle ABC with the angle A is equal to 70 degrees, the angle B is equal to 80 degrees, and the side A that's equal to 12 centimeters. We're supposed to find the measures of angle C and the sides B and C. Okay, so, and again, we're going to follow our normal naming conventions where we name our angles with a capital letter and the sides opposite the angle with the same lowercase letter. The first thing I would suggest that you do is go ahead and draw the triangle. That's always your best plan of attack. From here, what you're going to see is that you have what I like to call an anchor. That is, I know little a and its angle, big A. When you have the corresponding side and angle, then you know you can set up the law of sines. So that's what I would do first. Draw the triangle and then find your anchor. So we can set up the law of sines to find side B. So I would use my anchor, little a divided by the sine of A is equal to little b divided by the sine of B. You could cross multiply to solve. We can get multiply the sine of 80 degrees over to the other side. And this leaves us with 12 times the sine of 80 degrees is equal to b times the sine of 70 degrees. If you divide both sides by the sine of 70 degrees, you will get little b alone, which is about 12.6 centimeters. So now we're going to know that little b is actually 12.6 centimeters. The only things that we have left to find are little c and big C, the angle. To find the side little c, it's actually pretty easy. It wouldn't be difficult to calculate what that missing angle is. It would have to be 30 degrees because there's 180 degrees inside of a triangle. Thus, finding angle C just means you're doing 180 minus 80 minus 70, and that leaves you at 30 degrees. So finding angle C is pretty simple. And we can just set up the law of sines to find that little c. Again, use your anchor. We were given that little a was 12 and that angle A was 70 degrees. So it makes sense to continue to use that part of the law of sines. Little a divided by the sine of A is equal to little c divided by the sine of big C. And we can cross multiply to solve. Sine of 30 degrees times 12, sine of 70 degrees times c. And we can divide both sides by the sine of 70 degrees. That will give us little c alone. You can pop that bad boy into your calculator and you're going to get 6.4 centimeters. And there it is. You have solved the triangle. We know angle A, B, and C, and we know sides A, B, and C. Note that I used the given values of A and little a in both of our calculations. Your answer is more accurate if you do not use rounded values in your calculations. So also, if I would have made an error somehow in my calculations, using the side and the angle that they gave me in the problem makes it more likely that I would at least get some parts of it right. You want to be able to gather those points up everywhere you can. Let's try another one. So here's example number 2. This time we're given the triangle A, B, and C with angle C is 115 degrees, angle B is 30 degrees, and side A is 30 centimeters. Then we can find the measures of angle A, sides B, and C. Finding angle A isn't going to be too challenging because they did tell us 2 of the angles already. So it's going to need to add up to 180 degrees. To solve for the missing sides of the angles, we must have an angle and the opposite side. I call that the anchor. We must find angle A first because the only side that's given is side A. So right now, I don't have an anchor. I don't have 30 degrees and then directly across from it a little b. I don't have 115 degrees and then across from it a little c. And I don't have angle A, even though directly across from it I have 30. So we've got to find angle A first. Since all the angles are going to add up to 180 degrees, I know angle A is going to be 35 degrees. So we can put that in there, 35 degrees. Now that we have an anchor, we can actually go ahead and set up the law of sines to find our other sides. It doesn't matter if you find little b first or little c first. I'm just going in alphabetical order at this point. So I'm going to find little b first. So I use my anchor. 30 divided by the sine of 35, little a divided by the sine of big A, is equal to, and here I've got little b divided by the sine of big B. And again, we're going to use the opposite operation to isolate our variable b. So you could cross multiply and then use division to get little b alone. Pop this into your calculator and you'll get that little b is about 26.2 centimeters. So now that we know that, let's go ahead and set up the law of sines to find little c. We can use our anchor that little a divided by the sine of big A is equal to little c divided by the sine of big C. Use the opposite operation to isolate your variable c. And we're going to divide both sides by the sine of 35. Pop that into your calculator and we get 47.4 centimeters. And I'm going to give you a little heads up. What you want to really make sure is that while you're working on problems in degrees, that your calculator's in degrees mode. You definitely do not want to do this and get it all wrong because your calculator is in radians mode. So please, please make sure you're in the appropriate mode. And there you have it. We've solved for all the missing angles and all of the missing sides. Use the law of sines whenever you're given two angles and one side. The situation where you're given two angles is for certain the easiest of ways that you can use the law of sines. And that's what I have for you today. I hope that you've enjoyed this lesson and that you're feeling pumped to learn about lesson 4.6 and using the law of sines some more. Have a great one. Bye.